Section 3.3, orthogonality. Orthogonality simply means being perpendicular, or for two vectors making a 90-degree or pi over 2 radian angle. In the previous section, we learned that the angle between u and v in any space Rn is defined to be theta. The angle is cos inverse, or arc cosine of u dot v over norm of u, norm of v. And the reason that this definition makes sense is the Cauchy-Schwarz inequality that says what we have here inside the braces, inside the brackets, is going to be between -1 and 1. Otherwise, this wouldn't be defined all the time. But since what we have inside the brackets, according to Cauchy-Schwarz, is always between -1 and 1, this definition makes sense for Rn. So from this definition, you can see that if u dot v, if the product of the two vectors u and v, if that product is 0, then theta would be cos inverse of 0, and cos inverse of 0 is pi over 2. That means if the dot product of u and v, or v dot u, doesn't matter, if that is 0, then this is equivalent to theta, the angle between the two vectors, is pi over 2. So two vectors are orthogonal if and only if their dot product is 0. Any questions so far? So here we have two definitions about what is an orthogonal set and what is an orthonormal set. A non-empty set of vectors in Rn is called an orthogonal set if all pairs of distinct vectors in that set are orthogonal. So a very simple example of that would be, imagine we have these three vectors. U is 2, let's say 0, 0. V is 0, 3, 0. And W is let's say 0, 0, 4. Yes. If I take U, V, and W, and I put them in one set, I'm going to call that set S. Put U, V, and W, these three vectors in that set. Then, since each two of these three vectors, if I pick any two of them, they're orthogonal to each other, then that would be an orthogonal set. So if I multiply u dot v, it's clear I'm going to get 0. If I multiply u dot w, I get 0. And if I multiply v and w, I also get 0. So that makes the set S an orthogonal set. Make sense? So what I'm giving is a trivial example of an orthogonal set. And what is an orthonormal set? It says an orthogonal set of unit vectors is called an orthonormal set. So if you just think about the rows of the three rows of I3. So I3 is 1, 0, 0, 0, 1, 0, 0, 0, 1. If you think of each row as a vector, so we have this vector, and we have this vector, and we have this one here. And it's clear that these three vectors are orthogonal, each two of them. If you do the dot product, you're going to get 0. And also each one has a length of 1. So these are unit vectors. Basically, this is I, the standard unit vectors, and this is J, and this is K. These are the standard unit vectors. So if I put these three into a set, that set would be called an orthonormal set, because all the vectors are mutually orthogonal with respect to each other, and each one is a unit vector. Again, this would be a trivial example of an orthonormal set. Is that clear? What is an orthogonal set and what is an orthonormal set? Okay. Example 1, show that these two vectors are orthogonal. If I want to show that these two vectors are orthogonal, the only thing I need to do is to multiply them using dot product. If that dot product is 0, then yes, they are orthogonal. If that dot product is not 0, then they're not orthogonal. Actually, if u dot v is positive, then automatically it means that theta is going to be acute. And if u dot v is 0, then theta is exactly 90 degrees or pi over 2. And if u dot v is negative, then theta would be obtuse. So I'm going to use this. I'm going to multiply them and see what happens if I multiply u and v. So the dot product of u dot v in this case is going to be negative 2 times 1. That's the product of the two first components, and then 3 times 2 plus 1 times 0. And finally, the product of the last two components, 4 times 0. That's going to give me negative 2, 6, 0, and okay, it's 4 times. Let's do that again. U dot v negative 2 times 1 plus 3 times 2. Then the third components, I multiply them, 1 times 0. And finally, I have 4 times minus 1. That's going to be negative 2 plus 6 plus 0 minus 4. And you can see this is 0. Yeah. So that means u and v are orthogonal with respect to each other. Any questions? Okay, now we're going to use this. An application of this would be a special kind of representation for a line in R2 or a plane in R3 called the point normal equation. So we can use orthogonality to represent lines in R2 and planes in R3 in a form called point normal equation. So I want to emphasize here that what I'm going to teach you about point normal equation, it is only useful to describe a line in the two-dimensional space on the xy plane or a plane in the three-dimensional space, the xyz coordinate system. So I cannot use this to describe or to represent a line in R3 or a line in R4 or a plane in R4. It's very limited. Yes, only used for lines in R2 or planes in R3. Okay, so in R2, I want to argue that if you know one point, so every line in R2 is completely specified by one of its points, say the point P0, X0. So let's say this is the point P0, P, the point P, X0, Y0. Let's call that P0. P0, X0, Y0. And a vector n, which is called the normal vector, that is orthogonal to the line. So let's say this vector is over here. Let's say this is n. It's a vector, let's say AB. So I want to argue that any line is fully specified, is completely specified by a point on that line and a vector orthogonal to the line. So now use your imagination and or you don't have to use your imagination. You can actually use the annotation tool of Zoom and draw the line. Can somebody do that for me? Draw the line that passes through this point and is orthogonal or perpendicular to the vector that I have specified, the vector n. We want to see whether we have agreement here. And my point is to show you that there is only one way you can do that. There is only one line. So this is enough information to describe a line. Okay, I'm going to do that myself. The line would be this. No, it has to pass through that point. It has to pass through the point P0 and be orthogonal to the vector n. And since there is only one way to draw that line, there is only one line that passes through the point P0 and is orthogonal to the vector n, my argument is that this is enough information to describe the line. Is that clear? So if I have one point from a line in R2, and I have one vector that is orthogonal to that line, I can draw the line. Yes, I should also be able to find an equation for that line because it's a unique line. So how do we do that? I'm gonna call any point in the xy plane as P. Yeah, so or an arbitrary point on this line to be Pxy. Now think of the vector that goes from P0 to P. The vector that goes from P0 to P is this vector here. So you agree that for any point that is on the line, the vector P0P would be orthogonal to n. And for any vector that is not on the line, the vector P0P will not be orthogonal to n. So for example, if you have a point over here, and if I draw a vector, that vector will not be orthogonal to n. Yes, so a point would be on the line if and only if the vector P0P is orthogonal to n. So the point Pxy is on the line if and only if the vector P0P is orthogonal to the vector n. But we can write that down as an equation. That equation would be n times P0P is 0. Because two vectors would be orthogonal if and only if their dot product is 0. Yes? So now if I just expand that, this vector here is A, B, the dot product. The vector P0P is going to be terminal minus initial. So it's x minus x0 and y minus y0. So x minus x0, and the other component would be y minus y0. If I do the dot product, I get a times x minus x0 plus b times y minus y0 is equal 0. So what you see here, this equation is the point normal equation of a line in R2. It simply comes from the orthogonality of the two vectors, P0P and the vector n, which would only be the case if P is on the line. Make sense?
Sir?
Yes?
So for two vectors to be orthogonal, they need to be perpendicular for one another.
Yeah, orthogonal and perpendicular are the same.
Okay.
These are synonymous.
Okay. Thank you.
Sure. Any other questions? Okay, similarly, every plane in R3 is completely specified by one of its points, say the point P0, X0, Y0, Z0, and a vector, a three-dimensional vector ABC, called the normal vector that is orthogonal to the plane. Okay, so for this one, I downloaded a photo to show you. So think of this point here, the point P0, X0, Y0. So that, let's say that's the point on the plane. And this is the vector that is orthogonal to the plane. So you have a point P0, X0, Y0, Z0, and you have a vector called a normal vector like this, ABC. So my argument is that if you have these two information, then there is only one plane that would pass through this point and be orthogonal to this vector. So the plane that is shown in the image, that would be the only plane. You cannot think of any other plane that passes through this specific point and is also orthogonal to this vector. These two pieces of information, they fully and completely specify a plane in R3. So these two should also be enough information for us to write down the equation of that plane. So you can find other planes that are orthogonal to this. So any plane that is parallel to this plane would also be orthogonal to this vector. But there is only one of them that passes through this point as well. It's a unique plane. Or you may find infinitely many planes that pass through the point P0, but there is only one plane that passes through this point and is also orthogonal to the vector. So these two pieces of information completely specify and describe one unique plane. Now, think of any point on that plane. Let's call that point P, X, Y, Z, which is an arbitrary point from that plane. Now, imagine the vector that goes from P0 to P. The vector P0, P is going to be terminal minus initial. So X minus X0, Y minus Y0, and Z minus Z0. Now, if the point XYZ is on the plane, then the vector P0P and the vector N will be orthogonal. But if the point XYZ, the point P, if it's outside of the plane, then the vector N and the vector P0P will not be orthogonal. So I say that P0P is orthogonal to N if and only if the point P is on the plane. Or I can say it the other way around. I can say the point P, X, Y, Z is on the plane if and only if P0P and N are orthogonal. How do I write that down as an equation, a mathematical equation? Very easy. N times P0P using the dot product must be 0. Now, if I expand this, I get A, B, C dot product X minus X0, Y minus Y0, Z minus Z0 is 0. So my vector equation is going to be A times, I'm going to write it over here, A times X minus X0 plus b times y minus y0 plus c times z minus z0 is equal 0. So that would be the point normal equation of a plane in R3. Okay, so we have this. Both the line in R2 and the plane in R3 can be represented by the vector equation n times p0p, as I just showed here for the plane, and previously I showed the same thing for the line. It's not a different equation. For both of them, it's n times p0p is equal 0. In the case of the line, both vectors are two-dimensional. In the case of the plane, both vectors are three-dimensional, where p is an arbitrary point on the line or the plane, and n is the normal vector. So from now on, whenever you hear normal vector, you should think of the vector that is orthogonal. So if I say the normal vector to the line, I mean the vector that is orthogonal to the line. Or if I say the normal vector to the plane, I mean the vector that is orthogonal to the plane. So this one here, this vector n, is the normal vector, is a normal vector for the plane. Any vector that is orthogonal to this plane can serve as a normal vector. So the equation P0P times n completely specifies a line in R2 and a plane in R3 because it holds for every point on the line or on the plane, and it holds only for those points. The moment you have a point that is outside the line or outside the plane, then this equation will not hold anymore. If we denote an arbitrary point on the line x2, R2 with p, xy, then p0p for the line is going to have this form, and then this equation for the case of the line is going to be equivalent to this. P0p times n is 0, which you can write it like this. So if I say point normal equation for a line in R2 that passes, let's say, the point P0, x0, y0, and is orthogonal to the vector NAB, then the equation of that line is going to have this form. A times x minus x0 plus b times y minus y0 is equal 0. Similarly, for the plane, if we denote any arbitrary point on the plane like this, x, y, z, then P0P is going to be terminal minus initial. It's going to be this one here. And then if I expand the equation P0P times n equals 0, I'll get this one. So what we have over here. So I can say point normal equation for a plane in R3 that passes the point P0, x0, y0, z0, and is orthogonal to the vector n, ABC, is going to be like this. A times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. Notice that both equations are actually n times P0P is 0. Yes, if you expand it for R2, you get this. And the same equation, n times P0P is 0. If you expand this for R3, you get this equation here. Is everything clear? I'm going to give you some examples for R2 and R3. Example 2 is for a line in R2. Find an equation of the line in R2 passing through the point A for -1 and orthogonal to the vector n (3 minus 2). Okay, I just use the formula. It's going to be a times x minus x0 plus b times y minus y0 is equal 0. Now, what is a? This is a. What is b? This is b. These are the components of the normal vector. What is x0? X0 is the x coordinate of the point, and y0 is the y coordinate of the given point. So I just plug in. I get 3 times x minus 4 plus b, in this case b is minus 2, times y minus, I replace y0 with minus 1, so I get minus 1. Yes, minus 1 is going to be plus 1. That's it. I can expand this. I get 3x minus 12 minus 2y minus 2 is equal 0. And 3x minus 2y is equal, I get 14. So you all know that this is a line from R2, right? You probably are more familiar with the form, with the implicit form where y is isolated. So in algebra, we usually use the implicit form like this. And then y is going to be 3 over 2x minus 7. So you're probably more familiar with this form, which is called a slope-intercept, because you can now see that the slope of the line is 3 over 2, and it passes through the point 0 minus 7. So this form is called the slope-intercept form, and the form I just introduced is called the point normal form. Any questions? Okay. Let's look at example 3. Are we good about this example? Everything's clear?
Yeah.
Very good. Example 3. Find an equation of the plane that passes through the point A, -1, 1, 2, and is parallel to the YZ plane. Parallel to the YZ plane. So if you think of this as, okay, so X, Y, Z, the YZ plane would be the floor here. Yes, so that's the YZ plane. That's the floor here. So I can use the unit vector alongside the x-axis, which is the vector I, 1, 0, 0. I can use that as the normal vector, because basically I'm looking for a vector that is orthogonal to the YZ plane. So don't forget that if I have two planes that are parallel, then a vector that is orthogonal to this one, let's say this vector n, that is orthogonal to this plane here, I'm going to call that P1, it is automatically also orthogonal to the other plane P2 as long as the two planes are parallel to each other. Yes? So now let's go back to this problem. It says that the plane that we're trying to figure out the equation for passes through this point. So we have a point, but we are not directly given a normal for that. However, we know that the plane is parallel to the YZ plane. If the plane is parallel to the YZ plane, which is the floor here, then I can use the standard unit vector I as the normal vector to that plane. Because this plane is somewhere maybe up here or down here. It passes through the point -1, 1, 2, but it is parallel to the plane, to the YZ plane. So I'm going to use this as the point, and I'm going to use this as the normal vector. So what do I get? I get 1, that's A, so A, B, C. 1 times x minus 1, so x plus 1. So this would be my x0, this would be y0, and this would be z0. Plus 0 times y minus 1, plus 0 times z minus 2 is equal 0. So this is going to be 0, this is going to be 0. I get x plus 1 is equal 0, which I can also write as x is equal minus 1. That's it. That would be the equation of the plane. So the plane x equals -1 is going to be a plane that is parallel to the YZ plane and passes through the point -1, 1, 2. Generally, if you have, for example, x equals a constant, that's going to be a plane, and in R3, x equals a constant is going to be a plane that is parallel to the ZY plane. Or if I say y equals a constant, then this is going to be a plane parallel to the XZ plane. And if I say z equals a constant, that's going to be a plane that is parallel to the XY plane. Let me give you a more ordinary example for this one. So find an equation of the plane passing, say, the point -1, 1, 8, and orthogonal to the normal vector 2, 3, minus 5. So you just use the formula. A times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal 0. Let's plug in values. A is 2, x minus 1 plus 1 plus 3, y minus 1 plus minus 5. So let's use minus 5 times z minus 8 is equal 0. So I get 2x plus 2 plus 3y minus 3 minus 5z plus 40 is equal 0. I can actually move every number to the other side. I get 2x plus 3y minus 5z is equal minus 40 plus 3 minus 2. So I get 2x plus 3y minus 5z is equal, okay, so this is like a plus 1, so minus 39. Minus 39. So this would be an ordinary plane. It's a plane that passes through this given point here and is orthogonal to this given vector 2, 3, minus 5. And you know, since the beginning, we have been working with systems of linear equations, and now you can see that this is a linear equation here. So since day one, I told you that these equations in 3 unknowns, these are actually planes from R3. And we talked about the geometry of, for example, what happens when you do row operations. For example, when you're doing a swap in the Gauss-Jordan elimination, you're not changing the position of the planes or the orientations of the planes. If you're multiplying a row of the matrix by a non-zero number, again, you're not doing anything in the geometry of those planes. However, when you're adding a multiple of one plane to another plane, then you're doing a pivot operations. So one plane begins rotating along the line of intersection between the two planes. So I've been telling you that these are planes, and now you can see why. This is basically a point normal equation of a plane passing through this point and orthogonal to this vector. Another thing I want you to notice is that when you have a homogeneous equation, like you have, for example, 2x plus 3y is equal 0, and let's say this is a line in R2, then this would be a line that passes through the origin because the point 0, 0 satisfies this equation. Or if you have 2x minus 3y plus z is equal 0 from R3, a homogeneous linear equation, then that would be a plane that passes through the origin because the point 0, 0, 0 satisfies the equation. So this here is a line that passes through the origin and is perpendicular to the vector 2, 3. And this one would be a plane from R3 that passes through the origin 0, 0, 0 and is perpendicular to the vector 2, negative 3, 1. Just A, B, C. Are we good? Okay, I'm going to stop here. The